So in this video, we're going to talk about finding initiation interval constraints through a brute force algorithm. So if you remember from the last few videos, we've been analyzing the access pattern of this simple example function, where we go from I equals 2 to 5, setting ai equal to ai minus 2 plus 1. And last time we found constraints on execution times of successive iterations of this loop by fully unrolling the loop and checking which iterations access the same memory locations. And this time, we're just going to formalize that process into a dumb but usable algorithm for this procedure that's going to work for fixed bound loops. And then later, we'll look at what's wrong with this algorithm and a more general algorithm for finding initiation interval constraints. So the idea of our dumb constraint finder is that we need to find every loop iteration that writes a value that's read by some later iteration. So for every iteration of the loop that writes a value to memory, we're going to check every subsequent iteration to see if it reads to the same location, and if it does, we're going to add a constraint which says that this iteration has to finish before the reading iteration starts. So we need to answer a few questions about our simple loop. The first one is, how many times does it execute? What is n, the trip count of the loop? And what's the value of the index variable I at iteration k of the loop? So just to remind ourselves, the loop is for int I equal to 2i less than 5, I++, and then this inner statement. So the loop is going to execute 3 times, right? We're going to have the I values 2, 3, and 4, and then when we get to 5, we'll break out of the loop. So at iteration 1, we have I equals 2, at iteration 2, we have I equals 3, at iteration 3, we have I equals 4. So in general, we can use this notation, I underscore 1 is 2, I underscore 2 is 3, and I underscore 3 is 4. And in general, I underscore k is k plus 1. So here's a pseudocode for our brute force algorithm. For k in the range 1 to 3 inclusive, for j in the range k to 3 inclusive, if an instruction in iteration k writes a value that an instruction in iteration j reads, then add a constraint that the instruction in k, or the kth instance of that instruction, has to finish before the jth instance begins. So we can write this like so. There's only one instruction in each iteration of the loop, so we can say if aik equals aik minus 2 plus 1 writes to a location read by ai sub j equal to ai sub j minus 2 plus 1, then we add this constraint. And we can simplify that into this formula of ak plus 1 equals aak plus 1 minus 2 plus 1 writes to a location read by, and then this expression. And we've really just substituted in our formula that describes the value of the kth and jth iterations of the index variable from the last few slides. So we can simplify this down even more. And actually, we can simplify this down even more because really this instruction only writes one location, the location ak plus 1. And this instruction only reads one location, and that's the j minus 1th location of a. So really we can say if k plus 1 equals j minus 1, then we add this constraint. Or more generally, we can simplify to if k plus 2 equals j, then we add the constraint that the kth instance of the body of the loop has to finish before the start, oops, excuse me, that should be the jth. Sorry. So this should be start of sub j of the loop body. And we can simplify this down using our instruction start and completion time formulas to this, which is that the end of the instruction in the loop plus the initiation interval times k minus j has got to be less than or equal to the start of this iteration in the ordinary basic block schedule. So if we execute this algorithm manually, what we're going to find is that k plus 2 equals j only when k equals 1 and j equals 3. And what that means is that the first iteration of the loop, k equals 1, writes a value written by the third iteration. And that's exactly what we found intuitively in earlier videos, right? So basically there's a dependence between the first iteration, where I equals 2, and the third iteration, where I equals 4. So next time we're going to talk about what's wrong with this brute force algorithm and what we can do better. And hopefully one thing that you can see immediately is wrong is that this algorithm doesn't even work unless the loop has a fixed number of iterations. But there's some other problems with this algorithm that we're going to talk about and that are going to allow us to produce a much simpler procedure for figuring out the dependence distance or the initiation interval execution constraints. And we'll talk about that in later videos.